Okay, let's just jump in. We've got our agenda today is to wrap up the intertemporal resource allocation idea. Just like in almost everything else in economics, you want to be equating marginal values. We want to be equating some kind of marginal benefits and marginal costs. And when you wind up at a point where you're doing that, where you are equating marginal benefits and marginal costs, then then you are at an optimal solution. So this rule for our intertemporal problem, that's captured by this rule here. Marginal net benefits in period 1 equal to the present value of marginal net benefits in period 2. The choice, because it's a 2-period problem and our resources are scarce, the choice is how much to consume in period 1, and then how much that will automatically imply some amount left over in period 2. So really it's like we have one choice, period 1 consumption, and then period 2 consumption will just follow automatically from that, because the resource is limited inherently, and you have whatever's left over in period 2 is what you're going to eat, what you're going to consume. So if you think about that, the choice is of period 1 consumption. So you have benefits, marginal benefits in period 1, and then the marginal costs in period 1 are what we have on the right-hand side of this equation. Those, you can think of those as like the marginal costs. Those are like the costs of your period 1 consumption decision, because remember, the resource is limited. Anything you consume now, you're going to be sort of implicitly taking it away from what you have remaining in the future. So your benefits, your marginal benefits, are kind of here on the left, and you can almost think of these as like your marginal costs. It's like what you're giving up by making a choice to consume something in the future. Okay, so this is just another application or another way of framing this standard marginal benefit equals marginal cost kind of rule. And as we saw last time, what that implies is we choose some allocation here where those curves intersect. That's the graphical meaning of this equation, MNB1 equals PV MNB2. The graphical meaning is that you find the point at which they cross. You note that implies 150 units in period 1 and only 100 in period 2. So in that case, that's the efficient way to allocate your stuff between period 1 and period 2, given the resource scarcity and also the discount rate. And the discount rate is sort of implied in this graph in terms of how far this MNB2 curve gets shifted down. A higher discount rate will shift that down further and sort of scale it down further, rotate it more and more counterclockwise. That's a higher discount rate. A lower discount rate will have it be closer to the original curve that was undiscounted. So that's something to keep in mind as we think about this problem. We talked about the optimal solution. We just talked about how 150 and 100 is an optimal solution. We call that a dynamic equilibrium, because it accounts for not just the benefits now, but also the benefits later. So it's dynamic. It's accounting for future time periods. And we talked about how that maximizes, the total combined area underneath these curves. We saw that was different than the static equilibrium. Remember this static equilibrium, MB equals MC, that was the static equilibrium. Choosing that equilibrium, remember that was at 250, or that was at 200 in period 1 and 50 in period 2. And we talked about how the total benefits associated with that were, the area A1 plus A2 plus B1. That's the area below your second period marginal benefits between 0 and 50. And the reason it stops there, again, is because if we're consuming 200 in the first period, we only have 250 total units. So there's only 50 remaining in the second period to consume. So our benefits are only going to be represented by the area below this curve up until 50 units. So we miss out on area B2 by consuming that extra 50 in period 1 rather than leaving it for period 2. So that's just a comparison between the static equilibrium, kind of the myopic, the choice that's only concerned that's only concerned with maximizing present benefits. That choice, as we just saw, is going to miss out on some important benefits by virtue of being a little bit too focused on the present. The reason that's inefficient is it only considers the first period, and it doesn't consider the inherent scarcity of the resource. It doesn't consider the fact that anything that you consume in the first period is going to chip away at the what you have available to yourself in the second period. I wanted to make just one point about discount rates here. So we had the original undiscounted marginal net benefit curve is given by this top kind of this top line here that I just superimposed a thicker line on top of. So this marginal net benefits, the one on top, that's the undiscounted version. And then as we start to discount that more and more, let's say, if we discount by 2%, then we're going to be scaling down every value of this top curve. We're going to be scaling that down. This first pivot, this first sort of counterclockwise rotation of the curve, that's associated with the 2% discount rate as opposed to 0. A further reduction from the original curve to 5%, that's going to be associated with a 5% discount rate. If our discount rate for some reason was 15%, then we would rotate that curve all the way down to the curve kind of that's level with that 15% number on the right hand side. So the higher the discount rate, the more that's going to bend down future benefits. And notice interestingly what happens with that is, at a discount rate of nothing, you have an even split between the two periods. And then as you discount more and more, so the 2% discount rate, that's going to be associated with this point of intersection right here. The 5% discount rate is going to be associated with the intersection point here. The 15% discount rate is going to be associated with the intersection point right here. So for each of these different discount rates, these are actually going to imply a different allocation between periods. As the discount rate goes up, it actually is going to imply that the optimal shift is going to be towards period 1 consumption. You're going to increase period 1 consumption and decrease period 2 consumption. So that gets more and more stark. The allocation shifts more and more away from period 2 and more toward period 1 as the discount rate goes up. Because remember, the discount rate sort of diminishes the value on future benefits or future returns. Okay, here's a question I want to pose to the class, because this is fundamental to this problem. We said that user costs are an externality in time. That was one of the ways that we actually defined user costs. That was one way of kind of thinking about user costs as an externality in time. It's, if you remember the formal definition, it's the opportunity costs of consuming something today. It's the cost of consuming something today, which implies that you have less to consume in the future. So consuming more today is, in effect, you're imposing an externality on your future self in a way. That's one way of thinking about it. So just as we, if we remember from our pollution example, we had our private marginal costs of producing something. We had our social marginal costs. which maybe could be represented by a parallel shift. Maybe in some cases they could be represented by a you know a rotation or some. There was some way in which we augmented the private marginal cost. We added external costs to get the social marginal cost. We can actually do that in the same way, remembering that user costs are just an externality in time, just the way that pollution externalities are. We can augment um, the supply curve in a sense to account for that user cost externality. And so the new supply curve, taking account of user costs, is going to be it's going to overlap with the supply curve until you get to 50, and then it's going to sort of increase at a steeper slope once you get to 50. So the supply plus user cost is sort of given by that red line that I drew over top of the other stuff, whereas the supply curve is just the constant black line that has the constant slope. Now, yeah, the question I want to pose to the class right now is why does it only start at 50? Why is there a kink here in the curve at 50? Why does it only start to slope up more steeply at 50 rather than immediately like what we had in our different pollution cases where these the social marginal cost curves sort of increased right away?
I'm not entirely sure how this works in real life, but in the example that we were looking at before, we didn't start eating into the resources for the next generation until we got to 50. And so like that's why the user costs don't really start getting added until you hit that point where you're like getting into the next generation's resources.
That's exactly right. Yes, that's precisely correct. I've got the static equilibrium here, right? So yeah, so Jackie's answer was exactly correct. We have a total of 250 units. If we're thinking about our period 1 consumption, let's say that we only go to 50 and we stop at 50 in period 1. That means that we have 200 units left over in period 2. And in fact, in the static equilibrium, 200 units is as much as we would actually want to consume and produce, because that's the amount that maximizes the benefits to society in a single period. And so until we get to 50, just as Jackie said, we're not actually cutting away into next period's consumption at all, at least in terms of what would be efficient. Because, of course we could consume more than 200, but it costs more than that. Once we get to 200, the marginal extraction costs start to exceed the marginal benefits, and it's no longer efficient from society's perspective to produce and consume beyond the 200 amount. So 200 is the efficient amount in any single period, and as long as we're staying at 50 or below, we can achieve that in the second period. And then once we go beyond that, then it's only then that user costs start to matter, because at that point we have to cut back from 200 in our second period. Okay. I have a slide here about resource depletion taxes, but I don't really care about resource depletion taxes. They're not that realistic, and I think they're just not that interesting. So I'm going to skip over this, and I'm going to get to this idea of scarcity rent. So remember that in the static equilibrium, we had marginal benefits equal to marginal cost in a given period, or I should say marginal benefits of consumption equal to marginal extraction costs. That's what the supply curve was sort of representing. So we consumed all the way to this point. Notice that the marginal profit, like the profit that the last few units of the resource earn, is very small when we go all the way to 200. The last few units earn very little profit. The gap between willingness to pay and willingness to supply, gets narrower and narrower, and eventually we get to a point where we get a price where price is exactly equal to marginal cost, and so those last few units of the resource earn the producers very little marginal profit. You could think of this from the perspective of a producer that, say, they own all this copper themselves, and they would like to try to get as much out of it as they can. They would like to try to sell it for as high a price as they can, and they know that it's scarce, and so they know that if whatever they sell today is not going to be available for them to sell in the future. We can consider what their optimal behavior would be, given that they want to try to maximize not just today's profits, but also the combination of today's profits and tomorrow's profits as well. Marginal profit is very small. If you are selling all the way to 200 units, marginal profit is very small because marginal extraction cost continues to rise throughout the period as you extract more and more. But notice that if you were to cut back a little bit and not go all the way to 200, you would actually be able to charge a markup. You'd be able to charge a markup because at 150 units, marginal cost is only, in this case, it's only 87.5. And at 150 units, people are willing to pay 112.5. So by cutting back, so right now, this is another way of thinking about the optimal allocation over time, is to think of it from the perspective of a resource owner that's trying to think about how to extract the resource optimally over time. If you don't go all the way to 200, if you stop before 200 and maybe cut back to 150, you're able to charge a little bit higher price because remember the marginal benefits, it's a curve, right? The marginal benefit curve is a curve, and the marginal benefits at 150 units they don't decline, they decline between 150 and 200, and so the marginal benefits are a little bit higher, and the willingness to pay on the part of consumers is a little bit higher when there's less available, and so you can charge up to 112.5. That's the price that the market will bear at 150 units. That's this price here. But your marginal costs are only 87.5. So you have a little bit of extra profit that you can earn because you're cutting back and not selling all the way to 200 in that period. And then remember, at the same time, you can take that profit, and remember, there's an interest rate. You have an interest rate. We had an interest rate of I believe it was 7.5%, 7.25% per year, and we were saying that this period in the future was 10 years in the future. So if you have these two periods, if you have this extra profit, which is the scarcity rent that you can earn in period one, if you have that extra profit, you can invest it. You can take that and invest it at 7.25% per year over 10 years, and you can make it grow and earn some return on that in some alternative investment. Okay. Now remember, you still have some of that resource left over to sell in the future. So if you look at the future amount that you have left, if you go only to 150 in the current period, you have 100 units left over in the present period, or sorry, in the future period. Your markup actually is going to go up. You're able to charge 75, or sorry, you're able to charge 125 because the units are smaller, like the quantity of units is smaller, and the willingness to pay is therefore a little bit higher because those units are inherently scarcer and are going to be used towards inherently more valuable things because there's just less of it available. So the willingness to pay is all the way up here at 125 when we have 100 units. The marginal cost is down here at 75. And so your scarcity rent, kind of the markup that a resource owner would be able to charge is greater in the second period because there's less available, right? And actually, you notice here that society actually doesn't mind that there's this scarcity rent, because remember, society knows that there's only 250 units available. From society's perspective, they would prefer that we conserve a little bit more in period one and save a little bit more from period two. And notice that that's exactly what's happening here. Um, from the perspective of the producer is going to naturally have some incentives to hold back production now because they know they can increase their scarcity rent or their net price in the future. That's part of the reason why I don't care about resource depletion taxes, because the incentives, we don't actually need them at all. The incentives naturally for producers are to cut back on current extraction and sale and save some for the future because they know that they're able to make a little bit more money. So in this case, as long as the property rights over the resource are well defined, um, you're going to have a case where producers are naturally not going to want to consume everything today, or not going to want to extract everything today and sell everything today. They're going to naturally want to cut back a little bit on their extractions today and save a little bit more for the future, because it helps them. It increases their scarcity rent, and it also helps society. Like, I mean, they don't care necessarily about helping society, but they do end up helping society, just through those actions of wanting to maximize their rents, wanting to maximize their scarcity rent, and hold back today in order to be able to sell it at a little bit of a higher price in the future. Okay. We had scarcity rent, which was given by the gap between the price and marginal cost. This is price and marginal cost. That's given by the gap between price and marginal cost. And it's relatively small. I mean, it's smaller in period one, that scarcity rent. Let me just point out, you can also think of this as the net price. The net price, that's the sale price of the resource, minus the marginal cost. So price minus marginal cost is like the net price. That's like the marginal profit that the resource owner earns. So net price and scarcity rent in this case are kind of the same thing. That net price, or that scarcity rent, is relatively small in the first period, because there's 150 units being sold. In the second period, there's only 100 units left, so the markup increases, scarcity rent increases, the net price increases, and we have a gap between price and marginal cost. That's actually, in this case, $50 gap between price and marginal costs. Okay, and let me just, before I talk about Hoteling's rule, let me just point out that this is exactly what we had just found. Let me just go back in time here. This $25 gap is the scarcity rent, the scarcity rent that the resource owner has by selling at a price of 112.5 and only having extraction costs of 87.5. That's the price and marginal cost which lead to this scarcity rent in period one. And then in period two, the markup is higher. They mark it up to 125 because they can, because there's fewer units available. People are willing to pay more because there's less available. 125 is the price the market will bear when there's only 100 units available. 75 is the marginal costs for those 100 units, or for the 100th unit rather. And so the scarcity rent in period two is 50. Notice that this is doubled. Notice that the scarcity rent between period one and period two has doubled. It's gone from 25 to 50. And if you remember, if we if you've been keeping score at home, we had a 7.25% interest rate, which was an annual interest rate, which compounded annually. And if you remember, our second period we were saying was 10 years after our first period. So this was our annual interest rate, which got compounded by 10 years. And that was roughly equal to 2. So notice that the scarcity rent here, the scarcity rent associated with the optimal allocation of copper between period 1 and period 2, the scarcity rent of the optimal allocation doubled between period 1 and period 2 from 25 to 50, which was exactly the rate at which their money would grow. If you had cash today and you invested it at 7.25% annually for 10 years, your money would double as well. So you have this matching of scarcity rent doubles, and that exactly matches the fact that your money would double in some alternative investment that was earning 7.25% per year. And it's that synchrony between scarcity rents and the rate of return on your money in an alternative investment. That's at the root of Hotelling's rule. Hotelling's rule says that the net price or the scarcity of a resource is going to rise in the optimal scenario where producers are behaving optimally. The net price or the scarcity rent is going to rise at the same rate as the interest rate, which is exactly what we have here. We have the scarcity rent doubling between periods, and we have your money doubling between those periods as well. If you had cash today, you could invest it at 7.25% annually and make it double over that time frame. So in a sense, this $25 scarcity rent in period 1, that's what the producer earns in period 1, above and beyond their marginal cost. That's the net price. That's the price minus marginal cost. They could take that money. They could take that $25, put it in the stock market, earn 7.25% per year over 10 years, and it would turn into $50. So in a way, what the resource owner is doing here is they're optimally trading off benefits now versus benefits in the future. If they have $25 of marginal profit today, they invest it at 7.25%, and it doubles, and it actually exactly equals what their scarcity rent would be in the future. So this example kind of looks at the problem from the perspective of a producer and shows that the producer is making themselves best off when they are holding back just enough to make the net price rise exactly at the interest rate, and that also is the rate of extraction that will maximize the net benefits to society as a whole. Because if we remember from our sort of our welfare analysis, 150 units in period 1 and 100 units in period 2 was the sort of the allocation that maximized optimal welfare for optimal total net benefits. And it happens to be the allocation which will also maximize, or at least it's the allocation at which producers will be optimally trading off the scarcity rents of the resource versus what they could earn in some alternative investment, given that the interest rate was 7.25% per year. And that's the core of Hotelling's rule. So Hotelling's rule says that the net price of a non-renewable resource under ideal conditions, when all the participants are behaving optimally, the net price will rise at the interest rate. And we've seen kind of a simple stylized example of how that plays out, where producers, if they know that they can get future scarcity rents that are higher than the ones today, they're going to hold back some of the resource from the market today, sell it in the future instead, and sort of maximize their own returns in doing so. And also sort of maximize the returns to society in doing so, because society doesn't want all the resource to be used up in the first period. They would prefer that some of the resource would remain in the second period. And the behavior of individual sellers of this resource actually, under idealized conditions, does lead to that same outcome. And that's what Hotelling's rule would predict. Okay, so that's kind of the end of the chapter 5 content that I wanted to bring up in class. It's tricky. Like I said, it's very tricky, and I have another document that sort of gives some more intuition for Hotelling's rule in a more in not just a 2-period case, but in a general, however long n period case, and also when there's competition between owners of a resource. It doesn't require monopoly ownership of the resource. This result still holds under competitive production of the non-renewable resource as well. And I explain that in the document. And if you're curious to know more about why that's true, you can read that, and maybe you're free to ask me questions about that if you wish. We won't get into anything that detailed on the exam in terms of the mechanics of Hotelling's rule, but the basics of it I've tried to outline here at the end of this lecture today.